so far with 3 new vulnerabilities. We will discuss in particular server-side request forgery, which is an attack where the attacker is able to exploit the web server as a confused deputy. So it's a privilege escalation attack. And the attacker forces the server to take action under attacker control. And in particular, this action is the communication of some HTTP request, which is going to affect some other server. Then we will discuss XML external entities, which is a less known attack, which abuses some functionality of the XML file format. And also, by using this attack, essentially we perform some form of privilege escalation, where we force the server to take some action which are controlled by the attacker. And finally, we will discuss about HTTP parameter pollution, which is a very simple attack, which can still be effective in some cases. And the goal of this attack is to confuse the web application on how parameters of the HTTP request should be parsed. And by confusing the application, we can force the application to follow some unintended behavior. This will complete our overview of server-side security. Again, we will not discuss database security because this was already part of the first module. Keep in mind when you think about real-world applications, you should always be concerned also about SQL injection, another form of database vulnerabilities, which we're not going to review in this part of the course. So let's start by discussing server-side request forgery, or SSRF for short. It's a vulnerability which allows the attacker to induce a server-side application to trigger some HTTP request. And the HTTP request is sent to some arbitrary host of the attacker choosing. There are many possibilities to carry out server-side request forgery. The classic scenario of server-side request forgery is dangerous because the server is forced to send this HTTP request to some backend server which is sitting on the same local network. So this local network is normally protected by a firewall, and so it's not directly...
Excuse me?
Yes?
Can you show the slides?
I'm not showing the slides. Okay.
No.
Okay, sorry.
Thank you.
Here we go. Working now? Okay. So as I said, server-side request forgery in the traditional view, the server is abused to let it communicate with some server which is normally not reachable by the attacker. In particular, because the server is either the local host or some backend server which is sitting on the same local network. As I said, this is the traditional way to think about the server-side request forgery, but of course there are multiple ways to abuse this vulnerability, and we're going to discuss some of these ways in the next lecture, in the next slides. First of all, to understand why the vulnerability is enabled, we should think about why server-side requests are common and popular. And to understand that, we have a very good example here. So we move back to Slack. And so we have this channel. And in this channel, you will see here that when I sent you some link to Google Meet, Slack is also rendering some information about what is the content of this link. Okay, and you can see in particular that this is some real-time meetings by Google. The way this is implemented is because when I send this link to Slack, Slack performs some server-side request to meet.google.com and fetches the content to provide me a preview. So this is a perfect example of a legitimate use of server-side request. This is not the only example. I introduce some more examples here. So we have this preview of resources, which is very common. You can find it on many messaging services like Slack or Skype. Try to send a link over Skype. You will see something very similar. But we have services which perform some form of caching or proxying, likely to preserve privacy of the end user or for performance reason. So it means that you don't communicate directly with the server you want to communicate with, but you have some intermediate proxy in between, which is firing requests for you, so that your identity, for instance, is preserved. Other common cases for server-side requests happen in the case of data import. So when you Google for some images, for instance, and you get the preview of the image in Google Images, you have an example of a server-side request, because Google is sending some requests on the server side before assembling the preview of the images that you get on the client side. And of course, there are possibly many other more use cases that you can try to think about. But the point is, server-side requests are popular, and we have tons of legitimate ways to use server-side requests. Of course, since this is a security course, we're going to discuss now how we can abuse server-side requests. To understand that, we start from this example here, where we exploit SSRF to attack the localhost, which is, as I said, the traditional application of a server-side request forgery. To understand that, let's think we have a system which is built on top of multiple servers. So in real-world web application, it's not uncommon to have a front-end server, which is a server which we interact with, and multiple back-end servers which deal with some tasks. So in this example, we have a front-end server which serves requests for www.foo.com. In particular, we can think that one of the request type which is handled by this service is the ability to collect stock information. So we can send, let's think we are deploying some e-commerce site, and so we can have a service which, given a product ID and a store ID, will reply to us by telling us the availability of the product inside that store. The way we implement this is by having the front-end server, and the front-end server gets the address, essentially, of the backend server, and the backend server is contacted by the front-end server, which eventually returns the response back to the client. So we have like three parties: the user who is interacting with the front-end server, the front-end server who is interacting with the backend server, and it is essentially acting as a proxy between the user and the backend. So in this case, let's assume the front-end server accepts POST request, and this POST request includes a single parameter, which is a stock API parameter you can see here. And the stock API parameter is essentially the HTTP request, which should be crafted by the front-end server to collect information about the products in a given store. So in this case, the content of the stock API parameter is HTTP :/stock.foo.com, and then we pass an encoded, as you can see, URL encoded string, which contains the product ID, in this case it's 6, and the store ID, which in this case is 12. Point is, an attacker can try to corrupt the content of the stock API parameter, so that rather than crafting a request which is sent to the intended backend server, the attacker could actually force the front end to forge an HTTP request to itself. So in particular, in this case, this is the malicious payload. Rather than contacting stock.foo.com, the attacker can force the front-end server to contact 127.0.0.1, which is the localhost. And so this request will send to the front-end server itself. Why is this dangerous? Because we might have some resources which are only accessible on the localhost, because for security reasons, they are not exposed over the web. So in this case, for instance, by crafting an HTTP parameter like this, what the attacker will be able to do is accessing the admin interface of the front-end server, which is normally not accessible from remote. It's only locally accessible from the front-end server itself. And so by crafting this particular parameter, the attacker is able to perform privilege escalation, because it will get access to some resource which is not intended to be disclosed to the attacker, but it's only intended to be available to the front-end server. And that's why I'm saying that the front-end server is acting as a confused deputy. So if you think about cross-site request forgery, which we discussed, in the cross-site request forgery case, the browser is the confused deputy, because the attacker is abusing the browser to send some HTTP request, which includes the user credential. In this case, the attacker is actually making the remote server act as the confused deputy, because this guy has some capability which the attacker does not have. In this case, the possibility to contact the local interface. Of course, this is not the only example where server-side request forgery is dangerous. For instance, we can try to use server-side request forgery to attack some backend server. In this case, the attacker is trying to corrupt the stock API parameter so that the request is not sent to stock.foo.com, but it is sent to some local IP address. So you know that 192.168.0 is representing a local network. So this local network is not visible to the attacker, right? But the attacker can try to abuse the front-end server, which is sitting over the same local network, to make a communication to collect the admin interface, in this case, not from the front-end server itself, but for instance, from some other server, which might even contain more sensitive data. So this machine is not visible from the internet, but the confused server is sharing the local network, and so it's allowed to access it. This kind of attack has been forgotten for a while because people have been focusing on other kind of attacks. You probably understood now that we have a huge number of attacks on the web, so there are many vulnerabilities one might try to exploit. But server-side request forgery is getting a lot of traction nowadays because it allows the attacker to try to exploit IoT devices. So if you think about IoT devices most of the time are not reachable from the outside, right? But they're still sitting on your own network because, for instance, they're connected to the same access point you use. And so the attacker can actually try to attack some IoT device by exploiting the unique network access point, which is sharing the local network with these all devices. So it's an attack which is getting more and more popular nowadays. We have other variants as well. I presented two cases here. One case is when we use server-side request forgery to attack some remote server. In this case, we said that the goal of the attacker essentially was to abuse server-side request forgery to contact some host which is sitting on the local network of the front end. Instead, the attacker could try to let the front end contact some other remote service, which the attacker could contact itself. But the real problem here is that the attacker might want to hide, and so rather than trying to carry out this attack on a remote machine itself, the attacker could try to use this confused front-end service to send malicious HTTP requests to other servers. So for the attacker, it's easier to hide because the attacker essentially gets a proxy which is used to carry out attacks against multiple other services, which of course is also a potentially dangerous scenario. The last dangerous case I want to mention is that by using a server-side request forgery, the attacker might be eventually able to bypass the same origin policy. Of course, the attacker has no way to provide content for, say, foo.com, but by using server-side request forgery, the attacker could try to fool foo.com into fetching content which is controlled by the attacker over the attacker's control server and send this content back to the user. This way, for instance, if the confused server fetches some script from the attacker control server, what the attacker gets essentially is very similar to a cross-site scripting vulnerability, because the attacker is able to fool some benign web application into fetching malicious content from the attacker control server. So server-side request forgery not only allows the attacker to hide in the crowd, essentially, but also to bypass SOAP by fetching malicious content. I think that all this combination of potentially dangerous scenarios should have convinced you now that server-side request forgery is a very dangerous vulnerability. And if you suffer from server-side request forgery, it's much better that you fix it as soon as possible. Question is, how can we fix it? The negative news is that fixing server-side request forgery is in general complicated. So we can come up with very intuitive recipes to deal with server-side request forgery, but the problem is that many of these recipes do not actually work nice in practice. So you might easily come up with defenses which can be fooled by the attacker. The possibly simplest defense which might come to our mind is performing some blacklisting of host names and IP addresses, for instance, that we don't want our server to contact, okay? In particular, we discussed that server-side request forgery is particularly dangerous because we might try to fool the server into accessing the localhost. The localhost is identified by 127.0.0.1 or by the localhost string. And so we might say, okay, we will just filter out this dangerous IP address. We will filter out the dangerous string, which is called localhost. But the problem is that it is very difficult, as usual, to filter out all the possible malicious payload. We discussed this issue multiple times now, because we said that it is very hard on the web to be fully comprehensive on all the possible malicious attack payload, because the web is complicated and we have tons of ways to encode the same information. To let you think about this point, I want to mention a few interesting and subtle details in this slide. First of all, when we think about localhost, we typically think about 127.0.0.1. This is in a sense, canonic representative of the localhost. But some of you might not know that the localhost is actually an IP range. So it's not a single IP address, but every single IP address in this range, so from 107.0.0.0 up to 127.255.255.255, all these IP addresses are actually mapped into the localhost. So you can use any of these IP addresses to try to make that the front-end server contact the localhost. And if the front-end server only bans this well-known IP address, blacklisting will not work as expected. Another interesting point is that there are different alternative representation of IP addresses. For instance, by having this shorthand, we are actually representing the 127.0.0.1 IP address. You can easily verify that from here. So in this case, you can ping 127.1. As you can see, this IP address, which apparently looks ill-formed, is not ill-formed. This is actually working, and this is contacting my own machine. So we have different ways to encode IP addresses, and some of these might not be very well known to some site operators. Then we can try to have the attacker register a domain and make this domain resolve to the localhost. Once you buy a domain, you get control over the DNS record of the domain. So in particular, you can force this record to make the domain resolve into an arbitrarily chosen IP address, including this special IP address, which is only used for localhost. This way, you might bypass the server-side request forgery because you, for instance, allow any communication to the external environment, so you can't allow a communication towards evil.com, but once evil.com is resolved, the resolution is actually sent to some local IP address. So point is, you must check the IP address after name resolution if you are concerned about banning some potentially dangerous IP addresses, like local IP addresses. There are also other attacks. In particular, an attack which is quite popular and dangerous is the so-called double encoding attack. What's the idea of double encoding? Think about a scenario where you have a front-end server and a back-end server. Okay, so we have two servers, and both these servers perform an encoding of the HTTP request they receive. Sorry, a decoding, because I expect, of course, to receive URL encoded data. In a double encoding attack, what the attacker will do is picking some character and encoding it twice according to the URL encode syntax. Why is this dangerous? Because if we encode the payload twice, what happens is the following. The front-end server will perform URL decoding, but after the URL decoding, we still have encoded content, right? Because the encoding was done twice. And so this means in particular that if the front-end service was going to ban some IP addresses or some URL, the content will be still partially encoded. So this content might look fine to the front-end service because it doesn't look like 127.0.0.1, but it's still an URL encoded variant of this IP address. Once this URL encoded variant of the IP address is communicated to the backend server also performs the coding. And so this double encoded data is eventually translated into the local IP address, which we mentioned and we don't want to have. And so the attacker was essentially able to completely bypass the blacklist-based filter, which was sitting over the front-end server. And then we have another point which I really want to mention, and we will have more details in the next slide. The attacker can try to exploit some quirks in URL parsing libraries because URLs are extremely hard to parse correctly. This might surprise you, but if this surprises you, it's just because you don't think about the real full syntax of URLs. But before discussing about this point, I want to have a very small break now to let you ask questions if something is not clear on this part of the lecture. If you have a question, please unmute your mic and speak up. Otherwise, I will start presenting how we can attack URL parsing libraries. Okay. Let's try to understand why it's so hard to parse URLs. Problem is, the full syntax of URLs is a pain, okay? I show you one possible representation of the full syntax. What is also annoying is that this syntax is not mandatory. URLs have tons of optional components which you can omit, and we will have defaults for these omitted components. But this is a URL in its full glory. So we have the scheme part, like HTTP or HTTPS, for instance, colon / / as a separator, when we have this first part of the URL, which contains the authentication credential. So in this case, we are saying that we want to contact, for instance, a given IP address, and we want to present ourselves as user and providing a given password. Then you can use the @ sign to separate the credential part from the rest. We have the IP address that we might want to contact. This is a local IP address. Then you might have colon and the port. In this case, the port is 80 because we're using the HTTP protocol, and this is the default port of HTTP. And then you have a slash, and after that, you can put a path information. And after the path, for instance, you might even introduce a query string where you have parameters which are separated by the ampersand. These parameters are binding between a name and a value made through the equal sign. And then you have the hash sign in the end, which is followed by the fragment identifier. So as you see, although the URLs we use on a daily basis are very simple, the full syntax of URL is extremely complicated. What is particularly annoying about the syntax of URLs is that if you try to write down the syntax of URLs using some grammar, for instance, for any of you who attending the computability course with me, you're familiar with context-free grammars. Okay, we can express the allowed set of URLs by using context-free grammars. The problem is that the grammar which defines URLs is an ambiguous grammar. I don't know if you recall enough about computability theory and formal languages theory, but a grammar is ambiguous when for the same string, you can produce multiple parse trees. And this is the perfect case for URLs. To understand the point, let's look at a concrete example. Let's consider this URL. This URL, we have http://google.com #hat and evil.com. If you look at this URL carefully, you will notice that you have two possible plausible interpretations of this URL. One possibility is I'm sending a request to evil.com, and the part before the hat is the part which authenticates the user. So in this case, you can think about this URL as the request to contact evil.com and to present ourselves as google.com #. This is a plausible username, right? And this is one possible way to parse this URL. But if you look at this URL carefully, you will also notice that we have another possible way to parse this URL. In particular, we can think that this part here is defining the domain, so we want to contact Google over HTTP, and the part after the # sign is the fragment identifier. So we can think about this URL as a URL which refers to google.com, and in the fragment identifier, we have the string @evil.com. This is, of course, annoying. And this is not only the only case where ambiguities might happen. If you want to think about another case where ambiguity might happen, you will notice that in the syntax of URLs, we have the colon operator occurring multiple times. So we use the colon operator both to separate the user from the password and to separate the host from the port. So a smart attacker can try to exploit this ambiguity. What's the answer? So how should we parse this URL? The answer is the RFC for URLs, which defines the algorithm to parse URL. But as I said, this is not a traditional parsing, a straightforward parsing starting from a context-free grammar, because the grammar defining URL syntax is indeed ambiguous. So we have to check carefully that specification. We will find details on how this kind of URLs should be parsed. But as a matter of fact, if you check URL parsing libraries in the wild, you will find that different URL parsing library will parse this URL in two different ways. Some libraries will parse this as option 1, and some other libraries will parse this as option 2. If you're curious about this form of attack, I provide you a bibliographic reference of a paper which was presented at Black Hat, which focuses exactly on how we can try to exploit flaws in URL parsing libraries. So let's focus now on a second possibility to prevent server-side request forgery. We said, okay, blacklisting is a possibility, so we want to rule out all the hosts and IP addresses which look dangerous to us. The other option is we rely on whitelisting. So we block everything by default, and we only allow selected communications. In general, this is a more robust solution, right? Because you have a safe default, which is great in security. But for some application, you cannot just rely on whitelisting. If you think about the case of Slack, which we've seen, Slack is willing to preview the content for every other site we passed as a link inside the Slack chat. In that case, I passed to you the Google Meet link, but if I pasted there an Amazon link, that also will be rendered. So whitelisting is better from a security perspective. Of course, it cannot be applied on every single web application. In the case of Slack, this is not an option. But also whitelisting is not easy to deal with. In particular, the attacker can try to, again, play with the complicated syntax of URLs to fool the whitelisting approach. In particular, by implementing whitelisting, you have multiple ways to implement the defense. You can ask for a strict match, and that would be great. But many times you don't actually check for a strict match in the URL, but you just have some more relaxed requirements, something you require the URL starts with something or the URLs contain something. We see here possible ways where the attacker can try to induce confusion. So in this case, the attacker is presenting fake credentials. So in this case, let's assume that we have good.com in the whitelist, but evil.com is not in the whitelist. If we don't implement the whitelist checking with care, this URL might sound good to us. But the problem is that this URL is essentially sending an HTTP request to evil.com, because here we have a username, which is good.com, which will just be ignored by the attacker. Here you have a different variant of the same way, essentially to play around whitelist-based filters. So in this case, again, we have an URL which is pointing to an attacker control domain, which is evil.com, but we are putting in the fragment identifier good.com so that the whitelist-based check might notice the presence of this string and consider that this URL is fine. And of course, we have the true classic, which is creating fake subdomains. So if I'm sitting at evil.com, I can create arbitrarily subdomain of evil.com with some more level of nesting. So in this case, I'm creating first a subdomain, which is called com, and then I'm creating a second subdomain, which is called good. And so in this case, if the whitelist only checks that the URL starts with https://good.com, what we are actually achieving is a bypass, because we can force the server to contact a malicious subdomain which is controlled by the attacker. Of course, all the quirks in the URL parsing library, which I mentioned in the previous slide, work as well. And you can think about multiple ways to combine these tricks to cheat the filtering approach to prevent server-side request forgery. So nowadays, we don't have, let's say, completely robust solution to prevent this kind of vulnerability, especially because, as I said, this is a relatively new vulnerability. So it has been known for a while. It was not really particularly popular, but now it's getting a lot of popularity due to this possibility of attacking IoT devices. So people are actually studying this vulnerability right now, nowadays. Firewalls seems to me like the best solution to prevent this kind of issues, because you can actually put a firewall on your machine, which prevents you to contact some dangerous IP addresses. But of course, this also comes with its own issues, right? So it's important that we are aware about this problem and about possible bypasses. So be aware that if you implement some blacklist or whitelist approach to prevent server-side request forgery, you might suffer for this kind of flaws. Questions so far? Okay, if you don't have questions, I want to show you another way to bypass server-side request forgery checks. And this is a common bypass which is enabled by another vulnerability which is called Open Redirect. Open Redirect is a well-known web security vulnerability which is normally considered a low-severity vulnerability, so it's not particularly dangerous by itself. The problem of Open Redirect is that you might have a service which is willing to get some parameter and redirect the browser to any URL which is contained inside that parameter. That's why it's called an open redirect. So we have a service which essentially implements a redirection towards any site which is specified through some parameter. This is normally not a big deal, but can be particularly nasty when it is considered in the context of server-side request forgery. For instance, let's assume we have an open redirect vulnerability over the server of the backend, which is called stock.foo.com. This server will accept a path parameter, and whatever you send into the path parameter is essentially the content of the redirection. So if you send as a path www.google.it, you will be redirected to www.google.it. If you have this kind of vulnerability over the backend server in our running example, you can try to bypass any kind of filtering which was implemented on the front-end server by exploiting the open redirect. So in this case, let's have a look at the malicious attack payload. So the stock API parameter contains a request to the backend server, and we passed as the path parameter the address of the localhost. This is particularly dangerous because this completely bypasses filtering, which is performed by the front-end server. Let's assume the front-end server deployed filtering in a smart way. And in a smart way, I mean that only the backend server, stock.foo.com, is allowed to be contacted. In this case, the request which is included in the stock API parameter is indeed something which triggers a request to stock.foo.com. So from the point of view of filtering, this is fine. This is the legitimate endpoint of HTTP request which should be forced by the front end of the web application. The problem is that once we communicate with stock.foo.com, since stock.foo.com suffers from an open redirect, what we get is that the front end is redirected to the local IP address. So if we perform the filtering at this layer, essentially at this layer we are happy, but we still retrieve something from the localhost. And what we retrieve is eventually returned in the response to the attacker. So in this case, the attacker is still exposed to the administration interface. So this is an interesting case because it shows you that by combining two vulnerabilities, we are able actually to get a much more severe effect. So even a low severity vulnerability as an open redirect can become a high severity vulnerability when it occurs in the right context. So my take is, in general, don't estimate any form of vulnerability. Of course, we should prioritize patching high severity vulnerabilities, but it's always better to take a look into low severity vulnerabilities as well, because you cannot understand how this kind of low severity vulnerability can actually be exploited by a smart attacker. We're now ready to move to the second topic of the lecture. This is another form of attack, which is likely less known than server-side request forgery. And this kind of problem is called XML external entity. I don't know if you're familiar with XML, but XML is the so-called extensible markup language. It's a markup language much very similar to HTML. And indeed, HTML is defined on top of XML, which is a sort of a meta language, as the name says, to create other markup languages. So in this case, you can see an example of an XML document. you can see the structure of this document in a sense reminds you about HTML because the structure of the document is based on opening and closing tags. So this kind of XML document is creating a node, and the node has a sender, like Tov, a receiver, Tov, a sender, which is Gianni, heading, which is the subject of the node, which is a reminder, and then we have the body. In this case, the body is just a reminder to buy the milk. This looks like a lot like HTML, right? Due to this tree structure of the document based on opening and closing tags. And XML allows you to define what is the valid set of tags which we can use to create such document. So in this case, I wrote this XML document. This is, in a sense, well-formed because all the tags which I opened are also tags which are closed, and they're closed in the right order. So this is syntactically well-formed. But here you don't see anything which defines what is the real structure of a node. Because if I have an XML file which contains nodes, I want to ensure that nodes all include these all 4 fields: to, from, heading, and body. The way we can express this is by making use of another file, which is called the document type definition, or DTD, which essentially defines the structure of a valid XML file. To understand how DTD works, I show you an example on this slide. In this slide, I perform an inlining of the DTD, but it is also possible to put the DTD in a separated document and just have a pointer to the DTD inside the XML file. In this case, I directly include the content of the DTD in the XML file. And what I'm doing here is, as you can see, defining a document type definition. I call it node. And inside this, I define 5 different elements. I define the element node, the element to, from, heading, and body, which are all the elements which actually occur inside the XML document which you've seen so far. Here we're using the pcdata command to say that this information is essentially a string. I don't recall on top of my head the real actual semantics of this information, but this is essentially saying these are strings. And then what we are saying here is that node is an element which expects to contain inside itself 4 other elements: a to element, a from element, a heading element, and a body element. So by defining this DTD, I can say that this is the kind of document which I expect here. So far, so good. Problem is, DTD allows one to use a potentially dangerous feature, which is called entity. What is an entity? It's very simple. It's just a binding between a name and a value. For instance, in this case, by using the syntax bang entity, we can say that the keyword wife should be substituted by the string Gianni. So every time you refer to wife inside the XML document, you are actually performing a syntactic substitution of this string wife into the string Gianni, provided that you put enough syntax to let the XML document understand that this is indeed an entity. The way you do it is by putting an ampersand in front of the name of the entity and putting a semicolon at the end. So every time in the XML document you see ampersand wife semicolon, this is just a shortcut for the string Gianni. XML also allows you to define external entities. An external entity is still a binding, but rather than binding a value to a name to a given value, like a string, you actually bind the name to a URL. The way you do it is by using the system keyword inside the syntax of the entity definition. So in this case, I'm defining a new entity, which is called server. And every time I refer to server inside the XML document, this will be replaced by a URI, which is http://stock.foo.com. So you can actually collect content which is hosted on a remote host by using this kind of external entity. Point is, entities are dangerous. Not only external entities, which are the most known dangerous kind of entities, but even entities in general are dangerous. In the next slide, I show you a very funny example, which is the billion laugh attacks. What is the billion laugh attacks? Let's have a look. Here we define a DTD, which is called lols, and we create a first entity, lol, which is bound to the string lol. Here we define an element, lols, which is bound to a string, so nothing particularly interesting so far. What is more interesting here is the new entity, lol1, which we create. What is lol1 is an entity which is expanded in a concatenation of 10 entities which are called lol. So the string, the entity lol1, is eventually substituted by the XML parser inside lol, lol, lol 10 times. What's the problem here? The problem is that I can iterate this trick, and so I can create a new entity called lol2, and lol2 is obtained by concatenating the resolution of the entity lol1 10 times again. And I iterate this again, 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 and again. Let's try to understand what happens when we feed an XML document which contains a single lol tag, which contains the last entity of the chain, which is lol9. How many elements we will have inside lol9? Inside lol, we have a single element. Inside lol1, we have the concatenation of 10 instances of the first entity. So this is a string containing 10 times the string lol. What happens here is that any of this guy, lol1, is again a string which contains 10 occurrences of the string lol. So since we have 10 of these guys, we have 10 times 10 string which are obtained by substituting lol2 through XML parsing. So this is 10 lols, this is 100 lols, this is 1000 lols, up to 1 billion lols. So this is 10 to the 9. And 10 to the 9 is a big number for most XML parsers. And so in particular, you can mount a denial of service attack against your web application by trying to ask the web application to process this kind of XML document. So every time you have this kind of nested structure of expansion of macros, and essentially this is a form of macro expansion, right? You potentially introduce a form of denial of service vulnerability inside your web application. Let's move now to the abuse of the external entity. That was an entity which was not external, but still dangerous. Let's have a look now how we can abuse of external entities to mount attacks. We still use the running example from the previous part of the lecture. So let's assume we have this front-end service, which is willing to send a request to some backend service to collect stock information. So it expects a product ID, and it will reply back by telling us what is the number of items available for that product. The difference over the previous case is that rather than getting the URL of the stock service from the HTTP parameter, what the front end accepts is an XML document. And this XML document is very simple. It opens with a stock check tag and closes with a stock check tag. And inside we have a single tag, which is called product ID, which contains the identifier of the product that we want to check for availability. In this case, 381. We can try to abuse about this form of XML document, for instance, to try to steal some password file. In this case, let's have a look at how the attack payload works. We create a DTD, and this DTD makes use of an external entity. You can see we define an entity which is called XXE, and since we use the system keyword, we are saying that we can replace this entity XXE with a URI. The URI can also use the file scheme to refer to a file which is sitting on the local machine. So in this case, we have file : // This is the beginning of the URL. And then we have the name of the file that we want to access, which is /etc/password. So once we define this entity, it just suffices to mount the attack to create a well-formed XML file, which opens a stock check tag, which is also closed. Inside, we put a product ID tag, which is also closed. This is fine for our DTD. But then inside the DTD, rather than putting a product number, we put the external entity. So we use &XXE semicolon to let the XML parser replace the content of this string with the URI which we specified here. So rather than getting the product ID in the response, we actually get the content of the etc password file. Notice that the attack will not work if we remove the system keyword from here, because what we would get in that case will be exactly the literal string which contains file : // etc. By using the external entity, you don't actually bind the name of the entity to an external, to some given string, but you actually bind it to the content that you fetch through a given URL. So this is a traditional example of how XXE could be used to steal a local file from the machine. But there is a good reason why I presented this along with server-side request forgery. Because the kind of attacks you enable through XXE are essentially very similar to the kind of attacks you enable through server-side request forgery. Because if you think carefully, the attack is not that much different, right? We're essentially fooling a front-end server to fetch some content that we actually want. Be it a server which is sitting on the same local network, be it a local file, or even a remote server. Indeed, we can try to use XXE to perform a server-side request forgery. In particular, since I said that external entities can be bound to arbitrary URIs or URLs, what we can do here is to abuse of XXE to craft a server-side request which is sent to a local IP address of a backend server which is sitting on the same local network of the front-end server. So by defining an external entity XXE, which points to an IP address which is sitting on the same local network of the front-end server, we can actually perform the same kind of attacks we've seen for the case of server-side request forgery. One possible counter-argument to all this discussion is XML is not a popular format anymore. Back at the beginning of the 2K, XML was extremely popular. So every service on the web was essentially exchanging information through XML files. Nowadays, XML is a little bit less popular. A lot of people prefer to use other structures like JSON to exchange data in a structured way. But nevertheless, XML is still around. And it is still around somewhat in an implicit format because we still have many common file formats which are based on XML. So although we don't have a server which explicitly accepts HTTP requests containing information which is encoded in the XML format, we still have servers which allow for file uploading, which is indeed a very common use cases of web applications. But many of the file formats which we can actually upload are based on XML. if you think carefully, document formats like docx and image formats like SVG are just XML documents. So in this, I want to show you. In this case, I crafted an SVG image. I can open it with GDump. You can see this is an image, right? It contains a string, a totally 8 SVG, which is rotated. Cool point is that to create this image, I didn't use GIMP or any kind of image manipulation program, especially because I totally suck at using this kind of programs. What I did was much simpler. So what I did was just opening with a text editor. And if you check the content of this SVG image, this is just an XML document. So this is extremely simple. By using an appropriate SVG tag, you can put a lot of information therein. In this case, what I'm creating therein is just a single text node, which contains my string, totally 8 SVG. And then I put some position information, something like where the string should be placed, what's the fill color of the string, in this case it's red, and some transformation, which is essentially a rotation, because you notice that the string was rotated in the image. And so by writing these 6 lines of XML, I was able to actually craft an SVG image. And this is just standard for other file formats as well. So although your server is not accepting XML information directly, it might still be possible that it will accept XML information, which is eventually processed by some XML processing library and visualized on screen. If you are in this case, you might still be able to exploit XXE by uploading a format, an image in the an image expressed using the XML format. How can we defend against XXE? I put here a quote from the Art of War of Sun Tzu, not because I like it particularly, but because every security course has to put this quote at some point, so I want to put it right now. And the quote says that if you know the enemy and you know yourself, you need not fear the result of 100 battles. What do I mean is that this attack is not difficult to defend against, but you must be aware of the existence of this attack. Because if you're not aware of this, you might actually fall into this attack. So now that you know that XXE is potentially a problem, you should check the details of your parser. Many modern parsing libraries disable support for XXE. So in many parsing libraries nowadays, if you try to define an entity which contains the system keyword, this will be not accepted by the parser. Which of course is great because it solves the issue by design. You can relax this security restriction, but most of the time you really don't want to. What I want to notice is that depending on the specific library, this might not be true. And most importantly, you might have some attacks which are still enabled by entities like the billion laugh attacks, which we discussed. And so you should be aware on how you can configure your XML parser so that this kind of vulnerability is not a problem. For instance, you might typically configure your parser so that you disallow DTD definition inside XML files, and rather than processing an XML file which contains a DTD definition, you can use your own static, locally defined DTD. So that if the attacker tries to do something fancy, that will be rejected by your parser because that does not comply with the expected format of the XML file. So in general, this is an attack which is relatively easy to fix because most of the time you can actually deactivate all the potentially dangerous functionality. But notice that this attack is also technology dependent because it depends on your programming language, on the specific library in particular you use for parsing XML. So you should really check the manual of your XML parsing library to see the right way to disable these potentially dangerous features like external entity if needed. Now we are to the last attack, which I want to mention in this lecture. This attack is quite simple to carry out, but still this is a very effective attack. And this attack is called HTTP parameter pollution, or HPP. And this is a vulnerability which is enabled by the parameter parsing APIs of web programming languages. To understand that, if you're a little bit familiar with PHP, you know that you can actually access the name of parameters by using the following syntax. So in this case, you say, give me the content of the user parameter of the HTTP request which woke you up, and bind this content to the variable X. What is the problem? The problem is that, in general, an HTTP request might contain the user twice, the user parameter twice. I can have user equal to Alice, ampersand user equal to Bob. What's the behavior of this instruction when I have this scenario? Because in this case, I'm building essentially on an implicit assumption that each parameter will only occur once inside HTTP request. But since HTTP request can have an arbitrary format, the attacker could try to forge a request which violates this implicit assumption. Point is, what should we do as a web framework when we actually try to get the content of the user parameter and we have multiple occurrences of user? We have many plausible options. One option is we return an arbitrary occurrence, and by arbitrary, I don't mean random, but I mean either the first or the last one, depending on how my web development framework is implemented. Or I can try to make some sort of conservative decision and say, okay, you will get the list of all the occurrences. So if you get Alice and Bob as the content of the user parameter, you get a list which contains both values. Point is, this is not just a theoretical discussion. The truth is that this kind of behavior really varies a lot across different backends. I show you a slide which is not maybe completely updated and fully accurate, but this is just to give you the feeling of how this problem occurs in practice. If you are developing your application using ASP and you have multiple occurrences of the parameter, what you get by a call to the equivalent of the get function of PHP is all the occurrences of that parameter in the HTTP request, which are separated by a comma. If you use the same instruction in JSP or in Perl, what you get is that you get access to the first occurrence of the parameter. If you do that in PHP, you get the last occurrence of the parameter, and if you do that in Python, you get a list of occurrences. So depending on the specific web development framework you pick, and potentially even depending on your web server, you might get different behaviors for this kind of unexpected thing. And by unexpected thing, I mean getting the same parameter multiple times, bound to different values. This is particularly dangerous, I would say, because once you develop complex web application, it's not uncommon, as we said, that you have a front-end server and a back-end server. And it might well be the case that the front-end server and the back-end server are implemented using different programming languages. So it might be that the interpretation you get for the front-end server, which is developed in PHP, is different from the back-end server implementation, which was developed in ASP. So in general, this is a mess, and we should not underestimate HTTP parameter pollution, although this is a very stupid attack which any monkey can mount. Let's consider a simple example where HTTP parameter pollution is a problem. And to show you the example in a fancy way, let's consider an example which is very close to you. So we have the university server, and let's assume that the university server is hosting a PHP application which processes POST request. And the POST request has a very specific form, which has 3 parameters. One parameter, exam ID, in this case, which is bound to 12. The final mark on a scale from 18 to 30, in this case, it's 25. And the student ID, which is your matriculation number, 1, 2, 3, 4, 5, 6. I have a small question for you, so take a couple of minutes to think about this. And my question is, let's assume I want to pass all the exams with the highest possible mark, which is 30 in Italy. And assume also that you can manually input your student ID when you enroll to the exam. So when you enroll to the Security 2 course, you're actually asked to provide manually your student ID. Can you actually find a way to trick the university server to give you a final mark of 30 in the security course, although your marks will be actually much lower than that? So try to think a couple of minutes on how to mount this attack, and then we will see the solution. So think about an application which has a form where you write in the form the exam ID, say 12, and you write in the form your student ID, and then you click a button and you get enrolled to the exam. Then you solve your exam, and I make the grading through this kind of request where I actually put the final mark in. So you have control essentially over your student ID, but not on the final mark, which I will put on the web application. Does any of you have an idea on how to fool this exam registration system? If so, please unmute the microphone and speak up.
We can add the final mark after the matricular number.
Exactly. So once you enroll to the application, you don't actually provide your ID number 443256, but you also append to it the final mark, encoded, of course, with the ampersand as a separator. Why does it work? Because when I will craft the post request to give your final mark, let's say it's 18, the request will contain the final mark parameter twice, once with value 18, once with value 30, and since the backend is implemented in PHP, the last occurrence of the parameter, which will be the one which is taken by PHP. So you will register a 30 rather than an 18, which of course is much better for you, and also shows you that you understood how parameter pollution attack work. A real-world example now to tell you that this is not just a theoretical vulnerability, but it is a vulnerability which actually affected some real-world services. This is a very famous example from Blogger. And Blogger, as you know, is a service which lets you host your own blog, and then you can share whatever information you like on your blog. And Blogger suffered from HTTP parameter pollution vulnerability back then. And the key idea of the attack is to provide the parameter blog ID twice. Let's understand what's the idea of this application and how the attack works. The idea is the following. This is a functionality which allows you to add authors to a given blog. So you are the owner of the blog and you want to add another author to the blog. The way you do it normally is you provide your blog ID, you provide a security token, which is known only to you. So that's the way you authenticate to Blogger. Then you provide a list of authors by specifying the email address of these authors. And then you have this OK parameter, which is essentially a way to say, OK, I want to send an invitation to this email address. So the users can eventually accept to be authors just by clicking send link, which will be received by email. In this attack, we're exploiting HTTP parameter pollution. What's the key idea? The key idea is that we have a blog ID parameter which is bound twice. Once to the attacker control blog and once to the victim of blog. And so the goal of the attacker is to become an author of the victim blog. What was happening in Blogger was that the permission check based on the security token was performed on the blog, which was contained in the first blog ID parameter. So from the point of view of security, this request is fine to Blogger because we have a blog ID, which is the attacker blog, and the security token, which is indeed the correct security token for the attacker. So the security check will work because the blog ID has a token which indeed matches what is contained in the security token parameter. However, after performing the security check, another component of Blogger was actually giving access to the authorship functionality. And what happens is that after performing this security check, this request was forwarded to another component of Blogger, and that other component of Blogger was checking the blog ID as the second occurrence of the parameter rather than as the first occurrence of the parameter. So since the second occurrence of blog ID is bound to the victim blog, what the attacker achieves is that after passing the security checks by checking the attacker token against the attacker blog, the attacker forces the web application to send an invitation to be an author on the victim blog to the attacker email address. So the confusion on which occurrence of blog ID should be taken, which is performed by two different components of the same web application, is the key enabler of this kind of attack. So as I said, when you develop stuff using multiple programming languages, you might have this kind of confusion. And this is a perfect real-world example of an attack where this kind of confusion was abused. Again, we are lucky in a sense because also HPP is easy to defend against. Point is, you should know that it exists. Now you know that the attack exists, so you're prepared to take countermeasure against this attack. Again, the solution is specific to your programming language of choice or web development framework. So check the documentation to understand what's going on, or implement your own test to check what's going on. And notice that if the API is kind enough to give you back a list of parameters, you have all the information you need. So you can expressly require that the list has length 1, because if the list doesn't have length 1, you can refuse the HTTP request and return an error. So if you have an API which is smart and gives you back a list of parameters rather than saying the first or the last occurrence of the parameter, you already have all the tools to implement protection. If you are not so lucky and you use a framework like PHP, which is naturally vulnerable to this kind of attack, the strong solution is to parse the parameters manually. So rather than relying on this high-level functionality which is provided by PHP, you should implement your own parsing of the parameter and check that no parameters occurs multiple times. Of course, it's also a good solution to encode some characters like the ampersand to avoid the attacks which we discussed, including the attack on the exam grading system, which I mentioned. And I want to spend a couple more minutes now to show you a less known attack than HTTP parameter pollution, which essentially exploits the very same trick, but in a slightly different context. And this attack, which I like a lot, is called cookie shadowing. And cookie shadowing is essentially a variant of HTTP in the context of cookies. What's the idea of cookie shadowing? The idea is that cookies have a scope, and in particular, you can define scope based on the combination of the domain, secure, and path attributes. So you can define multiple cookies with the same name but different scope. For instance, Gmail is doing that. If you go in Gmail, you will notice that you have a Compass cookie, which contains some random values or some noise. But this Compass cookie is occurring twice. What's the key difference? These two guys agree on the domain and the domain attribute. So these are both cookies which are set by mail.google.com. They agree on the secure attribute, but they have a different scope because one of these cookies is set for the path mail, and the other one is set for the path mail/u/0. What's the problem intuitively? The problem is that if you send a request to mail/u/0, both these cookies will be sent, both this one and this one, because this cookie is sent to all the requests which are under this path. So it means that you have at least one endpoint which gets the same, a cookie with the multiple occurrences of a cookie with the same name. Of course, this is not a problem for Gmail, because in the case of Gmail, the content of these two Compass cookies is the same. So even if the server picks the first one over the second or vice versa, this is not a problem. What is a problem is when the value of these two cookies is different. And the point is that the attacker can actually force the value of these two cookies to be different, because the attacker can actually craft a cookie with the same name of a valid cookie and force this cookie inside your own browser. We said that cookie integrity is a problem on the web. We discussed also a solution on how to ensure cookie integrity. In particular, we discussed cookie prefixes and use of HSTS with the full with the include subdomain option activated. But in general, if we cannot trust the integrity of cookies, the attacker might be able to craft a cookie which has a different scope of a legitimate cookie but the same name. And by playing with this, the attacker can actually force an HTTP request to contain multiple occurrences of a cookie with the same name. What's the problem intuitively? That as we add a simple abstraction to collect the value of an HTTP parameter, we also have similar abstraction to access a cookie value. I can ask to PHP, give me back the value of the cookie called SID, but if I have multiple occurrences of the cookie which is called SID, what is the cookie which is preferred? This is not well known, right? And what is even worse is that this kind of problem depends not only on the client, but it also depends on the server. So in the case of PHP, let's assume that PHP always picks the last occurrence of a cookie when we have multiple cookies with the same name. Let's make this assumption. Now observe that it is possible that Google Chrome, Firefox, and Safari will send cookies in different order. So in general, there's a lot of confusion in the right cookie to pick, because the choice depends on both the backend server and depends also on the client, because different clients can put cookies in the HTTP request following different orders. So this is a variant of HTTP which is still performed in the case of cookies. I want to conclude this lecture with an example of a real cookie shadowing attack. So this attack was a credit card stealing attack against China UnionPay. And that site was using a single session cookie, which is called UCSKey. And the bad news is that by presenting that cookie, you could associate a credit card number to an existing account. This way, you could simplify future payment processes, because this is essentially what you do also on Amazon, where you store your credit card number on the Amazon session, and then you can actually buy from Amazon without providing your credit card number every single time. In this case, what the attacker could do was force his own value of UCSKey in the victim browser, for instance, by forcing HTTP traffic. And by doing that, the attacker was able to make the account association go wrong. This means in particular that the attacker could provide the credit card number to China UnionPay, but since the cookie which was picked by the server was the cookie of the attacker, the victim credit card was bound to the attacker session, and that let the attacker essentially steal the credit card information from the victim. And this attack was even worse than possibly expected, because there was no visual indicator of the account identity on the association interface. So the user had no legitimate way to realize that the credit card number was bound to the attacker session rather than to the user session. This is indeed very similar to what we discussed for HTTP parameter pollution, but in a slightly different context. I provide you a couple of bibliographic references here. First reference is the Black Hat paper which I mentioned, which tells you how you can try to exploit URL parsing libraries in common programming languages. And the other paper is a paper which I like a lot because it raised a lot of awareness into the cookie integrity problems. It was published in 2015 at Usenix. And they discuss why the lack integrity of cookies was a problem on selected real-world services. So it's a very nice read, so I hope you enjoy it if you're curious. And that's basically it for today's lecture. But if you have questions, I'm available for a few minutes.